one thing I'll suggest is that especially if it's loud on your end, you might want to mute it. You mute it from your side, but at any point, feel free to unmute and ask a question. Okay, so that you can. It should be interactive. Okay, so feel free to unmute at any moment. The goal of these sessions is to help you review for the Praxis. There's a lot of material on the Praxis, so what we're hopeful is that each person can take a different topic and get some review in that topic. So what I'm going to do tonight is mostly focused on functions, types of functions, and different operations on functions. So don't feel like this is the entirety of the material on the Praxis. It is far from it. It's just one particular piece that we're going to take the time to talk about tonight. Thumbs up if that sounds okay. All right. All right. So what I'm going to do is from a Praxis practice test, I'm choosing some problems that I'll put up on the board, and we'll kind of go through together. And then we'll use that as a chance to talk about some particular topics that we want to review as we go along. But we're going to start with problems in order to review what we need to review. Sound good? All right. So here is the first problem. First, and I want to make sure that I'm writing where you can see. It asks, what is the inverse of the function defined by y equals x to the fifth minus 3. Now, can y'all read that if I write it on the board like that?
Yeah, I can read that.
Okay, good. Now, the so can anybody chime in and remind me what it means to be an inverse function?
I don't know what it means. Undo, but I can see what you need to find it.
Okay. All right. So hold on to that for a second. Don't know exactly what it means, but you know what you do to find it. That's fair enough.
That's what I know. I know you like switch some stuff. I can find it. I just don't really remember what it means.
Okay. Yeah. All right. So let's think about what it means, and then we'll think about the process for finding it. So basically what we're saying, you've probably heard of like inverse operations. So for instance, what's the inverse operation for addition?
Subtraction.
Subtraction. Blake's got it. So yes, Melissa got it as well. I like it. The inverse of division is what?
Multiplication.
You got it. All right. So what we kind of think of with inverse is we think that one undoes the other. Okay. So when we are thinking about inverse functions, we should think about one undoes the other. So for example, let's just take this one right here. Let's say we put in the point, let's put in 2. So 2 to the 5th minus 3 is, anybody know 2 to the 5th off the top of their head? 32, good job. Y equals 29. Did I do that right? Some confirmation that I did it right. That'd be nice. So this particular function, what it does is it takes the number 2 and assigns it to the number 29, right?
Yep.
If you do another example, y equals 1 to the 5th minus 3, that's going to be 1 minus 3, so y equals negative 2. It assigns 1 to negative 2, right?
Yep.
The inverse function should undo that. the inverse function should take 29 and assign it to 2. Should take -2 and assign it to 1. Okay? So the inverse operation, or the inverse function, undoes the operations, or the operations of the function. Okay? So what we need to do is figure out how are we actually going to do that. So one thing we can do is, you guys probably know that a procedure, which I want to talk about in just a second. But if we think about this idea of undoing, you can really kind of get the inverse pretty easily. So if we think about going from x to y, if you put a number in for x, what's the first thing you're going to do to that number in this function?
To the 5th.
Yeah, raise it to the 5th power. Sorry, your friend Tyler was at the door wanting to come in and interrupt. Yeah, the first thing we're going to do is raise to the 5th power. Everybody agree?
I can't see you over there.
Oh, you can't see over there?
Not the X, no.
Okay. What if I turn it like this?
Yes, that's better. Wait, keep going a little bit more. There. Yes, I can see it now.
Okay.
Thank you.
So if we raise it to the 5th power, the first thing we do is raise it to the 5th power. What's the next thing we do?
Subtract 3.
Subtract 3. Okay. If we want to go from y back to x, we need to undo those operations, right?
Mm-hmm.
So what's the first thing you're going to do to undo those operations?
Add 3.
Add 3.
And then how do you undo raising to the 5th power?
Divide by. Oh,
No.
wait.
Keep
Don't ask me.
How do we do it?
Leslie, just chime on in.
How do you undo the 5th power?
I mean, I see the symbol. I just don't know what the word is.
What did you say, Blake?
5th.
5th root. There we
5th
go.
root.
5th root. There it is. I just can't hear it very well. We took
I saw the little root sign. I just couldn't think like what the word in front of it was. Just 5th. That's not hard. Anyway.
1/5
Typical
power.
student.
That's right. That right. Okay.
Yeah.
So the inverse function should say what? Well, in order to take the inverse function, you're going to add 3 to x, and then take the 5th root of that whole thing. And that's it. You with me?
And boom. There you go.
Boom. That's it.
Easy peasy lemon squeezy.
So you notice that it's the inverse operations. The operations were 5th power, subtract 3. It's the inverse operations in the reverse order. Is that okay? So you undo.
Can we do another example?
What's that? Do you say, can we do another example? Sure. So another example would be, let's say, let me move it over this way, Melissa.
Okay.
Let's say I have y equals let's do square root of x plus 2 divided by 3. Okay.
Do you have to do things in order?
The order
Like you
is
do
important.
going from X to Y?
Yeah, order is going to be important because
Okay.
the order matters for what your output is going to be. So the order is going to
Right.
matter for how to undo as well. Okay.
Okay.
Now, what are the operations you would do to x here? What's the first thing you do to x in this function?
Add 2.
Add 2.
There he is. Add 2. And then we would do, what would you do? Square root.
Okay.
And then what?
Divide by 3.
And then multiply.
Divide by
Divide,
3.
yeah.
So if we want to undo them, can I just avoid problems here by making this a cube root? Because it'll make my life a lot easier.
Oh, yeah.
All right.
Okay.
So if we go this way, then what do we need to undo? Instead, how do we undo these operations? What's that?
Multiply.
Multiply by what?
3.
And then what?
And
Raise to the third power. That's right. And then what?
Oh, dang.
Subtract 2.
Ah.
So if we start with an input x, we're going to multiply it by 3.
Yep.
Raise all that to the third power.
Yep.
And subtract 2.
Hot dog.
Okay.
all right, man. With it.
Now, Blake, you said you knew a method for getting this, right?
Yeah.
So if you started with y equals x, I'm going to come back over here unless tell me if you can't see. If you start with y equals x to the 5th minus 3, Blake, tell us what your strategy would be to do this.
So mine was just to switch the x and y variables.
So before we go on from that, he's saying the strategy is to reverse x and y. The reason is because that's what the inverse is doing, right? The inputs into your function become the outputs of the inverse. The outputs of your function become the inputs of the inverse. So the inputs and outputs are switching roles. So one way to sort of capture that is to just say, let's rewrite it.
Yep.
This is the inverse function. It's just implicitly defined as opposed to explicitly solved for. Okay? And then what would we do?
And then you just solve for what looks like x or something.
Yeah. So solve it for y.
Yeah.
And if you solve it for y, what are you going to do? You're going to add 3 and take the 5th root.
Yep.
Which is exactly what we got there, right?
Mm-hmm.
This will absolutely work. All it is a way of figuring out how you undo those operations. It's just an algorithm for undoing operations. Because what you're doing in solving there is exactly what we did here. We have to undo these operations on x, so you have to add 3 and take the 5th root. And that's what we got right there. That make sense? So if we went over here to this one, cube root of x plus 2 divided by 3, that strategy would say switch x and y, and then solve for y. So multiply by 3, raise to the 3rd power, and subtract 2.
So you literally pulled this off of a Praxis.
Off of a practice.
Yeah, so practice.
Okay.
So
I feel like I overthink half of those problems.
published by ETS. It's a Praxis published by somebody else, but
Okay.
yeah. Blake, you've taken it. So if you say if I give you a problem that you want to say doesn't look like anything you've ever seen on there, you just say the word.
But
Okay. Now, one more thing I want to say about inverse. Well, two more things I want to say about inverses, because and the second one will lead us into the next problem we're going to do. One is a function only has an inverse if it is 1-to-1. You remember the term 1-to-1?
Yep.
Okay. Can you tell me what it means for a function to be 1-to-1?
I can. Give me 1 second. Because we literally just went over this in linear algebra. Give me 1 moment. I mean, Friday in class. I mean, I know 1-to-1 means that every x goes to its own y.
That's well said. That's exactly right.
That's what I would have said.
Every input has to have exactly one output by definition of a function, right?
Yeah.
Mm-hmm.
But yeah, a function could do this.
No. Yeah, but it's not 1-to-1, right?
A 1-to-1 function would not. Every input. Now, if you think about this idea of switching inputs and outputs, that should make some sense. Because if we're going to create an inverse function, we should be able to reverse the direction of these arrows and it still be a function, right? If you have this, well, if you reverse the direction of those arrows, then you have one input going to two outputs, and that doesn't work.
Yeah.
So it has to be a 1-to-1 function in order to find an inverse at all. Okay?
Mm-hmm.
Other thing I wanted to say is another way to think about inverses is they undo each other. So if I have that function that we looked at a second ago, I'm going to write it in function notation. F of x equals x to the 5th minus 3. And we said the inverse function was the 5th root of the quantity x plus 3. Right? Well, I want you to notice what happens. Well, so for instance, we said if we started with 2, f mapped that to 29, and f inverse mapped 29 back to 2. We could check that out by saying f inverse of 29 is the 5th root of 29 plus 3, 5th root of 32, which is indeed 2. So it did what we wanted it to do. Okay? It did, you know, where the original function took 2 to 29, it does take 29 back to 2. Is that okay? So if we compose these two functions, what's going to happen? What'd you say, Blake?
You can get 1.
Get 1?
Yeah.
We can check and see. What we want to do is do f of f inverse of x or f of f inverse of x. In order to do that, our input is going to become the 5th root of the quantity x plus 2, right? Mm-hmm. Well, what is f of that quantity? It's going to be that quantity, the 5th, because this is our input, it goes in for the input, right?
Yep.
Okay. Minus 3. If I have the 5th root raised to the 5th power, what does that do?
You cancel each other out.
Yeah, so it's just x plus 3 minus 3, and so what's that give us?
Yeah, just x.
Exactly. Now this should make sense. Think about what you're doing. You're starting with x. You're applying f inverse to it and getting some output, right? Squiggle, the output. If we apply f to that, it should take us right back where we started.
Yeah.
Is that okay?
Yep.
So when we compose a function in its inverse, it should always give us back x. And you can see it the other direction as well. F inverse of f of x is f inverse of x to the 5th minus 3. So we take the 5th root of x to the 5th minus 3 plus 3. That's the 5th root of x to the 5th, which is just x. Okay? So when you compose a function in its inverse, it always just gives you the identity function, just x. Okay? Are there any questions about any of that before we went on? We kind of talked about a lot of stuff with that one problem, so I want to make sure we understand all that stuff before we go on to something else.
It's a deep problem.
Deep problem. We like deep problems, don't we, Alyssa?
Sometimes.
Okay. Awesome. All right. So you ready to do another problem?
Yep.
All right. So let me erase. So this question says if f of x equals x squared minus 4 and g of x equals 3x plus 2, then f of g of x or f of g of x equals what?
I love these, honestly.
All right, you're feeling good about it?
Yeah, if I could take this on the practice over and over again, I'd probably do well.
Yeah, awesome. All right, so tell me then.
I knew that was going to happen.
So tell me what to do then, Alyssa. You want to lead us through it?
So if f's going to be your other one, every time you have an x in f of x, you have to put what g of x is. So like where you have that x squared, you have to put 3x plus 2 in parentheses and then square it minus 4.
Exactly.
Right?
So you're saying we're just going to do f of 3x plus 2.
Mm-hmm.
So 3x plus 2 quantity squared minus 4?
Yeah.
Mm-hmm.
Okay. Now, this, I think that looks really good. Here are your 4 options for solutions on this problem because it's multiple choice. Okay. Oops. That's a 3.
Is just a swerve on there? Just a squiggle?
Yeah, that's a 3. That's a real 3.
Okay.
So which one of these is going to be correct then? What do we have to do?
Well, you got to expand the 3x plus 2 part.
Okay. So what is 3x plus 2 quantity squared then?
3x plus 2 times another 3x plus 2.
And that's just 9x squared plus 4?
No.
Good call. That's why they put this one here, to try to catch you saying 3x squared plus 2, 3x plus 2 quantity squared is just 3x quantity squared plus 2 squared. And then you get 9x squared plus 4 minus 4 is 9x squared. So that's where they're trying to catch you on that one. Okay?
Tricky practice. We see you.
Right. So you have to make sure and do 3x times 3x is 9x squared. You're going to get 6x and another 6x plus 4 minus 4. So we get 9x squared plus 12x. Did I do that right?
Yep.
Okay. Which one of those is right then?
No.
Any of them?
I mean, yeah, you can pull a 3.
The B.
Pull a 3 out. What else did you pull out?
Pull a 3x.
And what you be left with?
3x minus 4.
Plus 4, right?
Plus 4, yeah.
No.
Use test taking strategies here on this stuff when you're on the Praxis. Like if you're not, you can always multiply things out, right? You can work backwards from this as much as you can work forwards from this.
Yep.
So you can go both directions.
Okay.
Okay. All right. We feel okay about composition of functions?
Yes. Feeling great.
All right. here's an extension of a composition function. And the Praxis does have that. Not every question is necessarily multiple choice. They do have some like fill in the blank problems or open response where like you input a numerical answer.
Sure enough.
Yeah, Blake will confirm for us, right?
Yep.
Thank you, Blake.
So Blake's our experienced expert here. Veteran. That's right. He's been through the Praxis battles. So in this one, we are given f of x equals 3x and g of x equals 4 over x minus 1. What is the fractional solution of f of g of x equals g of f of x? Okay. So notice what this is saying, and then it asks you what you do here is fill in these two boxes. Okay. So,
Okay, go ahead. You got to be quiet.
if we, so here, you not just has to find the composition, you actually have to find two different compositions and then solve an equation involving them. All right. So let's start with f of g of x. Alyssa, since this is your thing, do you want to tell us what f of g of x is going to be?
All right, so f of g of x is going to be 3 times, is that 4?
Yes.
I'm sorry, it's a little
That's okay.
contrast problem here, but it's 4 over x minus 1.
Okay. Think so?
Right? Correct me if I'm wrong.
Anybody else? Looks pretty good to me.
Yep.
All right. What about g of f of x? What's that going to be?
4 over 3x minus 1.
We agree with Melissa?
Yep.
I think we should. So we have 12 over x minus 1 equals 4 over 3x minus 1. This is remember, this is 3 over 1, so multiply into the numerator. Okay. All right. What do we need to do to solve this thing then? Is the next question.
Do we solve for x?
Say again, Blake.
Do we solve for x?
Yes, we want to solve for x. So the question is how.
Is cross multiplication legal here?
Now, I'm going to go on record and say I kind of hate cross multiplication.
I'm not even genuinely surprised by that answer,
Yes, he does.
personally.
I've been on record about this several times. You're exactly right. Cross multiplication works here. I want us to understand why it works. Essentially, what we're doing is multiplying both sides by each denominator, right?
Yeah.
And what happens is we get x minus 1 over x minus 1 there. That makes a 1. We get 3x minus 1 over 3x minus 1. That makes a 1. And 1 doesn't make any difference.
Yeah.
Okay. So we're just left with 12 times 3x minus 1 equals 4 times the quantity x minus 1.
And then we're going to distribute and do all that mess.
All right. Tell me, Melissa, and then what's it going to look like?
36x minus 12 equals 4x minus 4.
You got it.
And then we solve for x.
Sounds like a good idea. So let's subtract 4 from both sides, 4x from both sides. We're going to get 32x minus 12 equals negative 4. 32x equals, I'll add 12 to this side and get 8. So x equals 8 30-seconds. Or if we reduce that then, 4/16 if you want, we can go all the way 2/8, 1/4, right? We probably could have gotten to 1/4 immediately, but I tried to torture y'all.
All of that for a fourth.
All of that for a fourth. Now you can double check and make sure it fits, but one easy way to check is like figure out what, do g of 1/4 and then plug that in, multiply by 3, and then do 3/4 and do g of 3/4, and then see if those two things match, and it should work out. So you're going to put 1. Sound good?
Nice.
All right. Any questions about that before we move on? No questions at all. Okay.
No, it was pretty.
All right. Let's use something entirely different. Okay. So this question says, for the point -2, -8, I'm about to where y'all can't see me, aren't I? On the graph of f defined by f of x equals x cubed. Give the coordinates of the corresponding point on the graph of G defined by G of x equals f of 2x. Okay? So the corresponding point on the graph of f of 2x. Now, there's a number of ways we could approach this problem. I want to use it to kind of review some stuff about transformations of functions. So in general, we might approach this in a few different ways in order to think about it. Can you tell me how the graph of G will compare to the graph of F?
Quick question. I can't see what the top two, the points are. Sorry. Just barely.
-2, -8.
Sorry. And I had to take a phone call, so I'm a little behind. But I got it. You'll keep going. I'm going to just mute myself while I catch up.
Okay. Sounds good. Can you two tell me how the graph of G is going to compare to the graph of F?
I honestly have no clue.
Okay. All right. Well, honestly, I don't like that answer. What's the question? What'd you say, Blake? I had trouble hearing you there.
Is it going to affect the amplitude or the what's the other word here? Is it because it's not going to shift it left or right or move it up or down? It's going to oh my gosh. There's some I'm missing one of these terms.
Okay. So it is a transformation of the function.
Yeah.
Now so you're going to be teaching this in your unit, so you got to get this down.
Yeah. Frequency?
Well, if you're thinking in terms of periodic functions,
Yeah.
this is not a periodic function. It's f of x equals x cubed.
Yeah.
So this is not a periodic function. Okay. There are some different things we can do to a function. The basic operations we can think about are addition or subtraction. Okay. Or multiplication, division. Is that okay?
Yep.
Now, let's think about what this is going to do to a graph. So one way to, a really good way to see this is to actually just let's play with a graph for a second. So I'm going to try to share my screen with you guys so that you can see what I'm doing. This one right here. Okay. So here, this is me on Desmos. Does this look all right?
Yep.
Okay. So what I'm going to do here is let's just define a function. Let's say f of x equals let's say I want to do like x cubed plus 3x. Let's see. Okay. Now, there's a few things I could do here. Let's say I'm going to do, let's do f of x plus some c value. Now you can see here, if I add something to that function, what does it do to the graph?
It shifts it up or down.
That's right. And that should make sense if you think about it. You're taking the outputs of the function, f of x, and adding something to every output. Everybody with me there?
Mm-hmm.
Okay. So if we're adding to the output, outputs are graphed vertically. So adding to the output shifts the graph up and down. Okay. What if I do f of x plus h? Well, now we're adding to the input, right?
Yep.
If I add something positive, notice what happens. Which direction is it shifting?
Left.
And here it's shifting right. Everybody with me there? Okay. So anytime I add something to the function, either to the input or the output, it shifts the function. So if I add or subtract, it's always going to shift the function. Okay?
Yep.
If I add to the input, it's going to shift horizontally. If I add to the output, it's going to shift vertically. Seem reasonable? Okay. All right. Now, one thing that's a little bit interesting here is that when I added something to the input, it shifted left, and when I subtracted something, it shifted right. So it sort of did the reverse of what I would expect, right? The reason for that is, well, if we just go to our function here, we can think about why that might be a little bit. So let's go to f of x equals x cubed. Let's say, ignore our actual function. Let's say I do f of x plus 3. Is that okay?
Yep.
If I look at the point -2, -8, well, if I put in -2 to this new function, I'm going to get f of -2, which we know is -8, and we're going to add 3, and that's going to be -5. So I'm going to get a new ordered pair, which is -2, -5. So basically, we added 3 to the output, and it shifted up. That seem reasonable to everybody?
Yep.
Okay. If I do it to the input, if I do f of x plus 3 like so, well, now if I plug in -2, now I actually have f of 1, which isn't something that is even related to my original point up there, right? F of -1 is not defined with the point I have. I mean, we could figure it out because we know the function, but it's not related to that specific point. So the question I'm more inclined to ask is, here we kept the input the same and saw what happened to the output. Let's now keep the output the same and see what happens. It looks like Gabby is going to join us, which makes me very happy.
It makes us happy too because we love Gabby.
We do. Roger, 1 second.
No problem, Gabby. Just feel free to unmute and chime in with any questions you want to ask, or you could type them in too, and I'll answer them as we go. Well, type them in, and then no mic or camera for Gabby. But if you type your questions in, I will be glad to answer them. So if here I'm going to say, let's keep the output the same. And the question is, for what input will we get back -8? Okay.
Can you scoot it over just a little bit?
Sure.
Perfect. Wait, nope. Up just a little bit. There you go, right there.
Okay. So the only way this gets to equal -8 is if the input into f equals -2, right?
Sure enough.
So I need x plus 3 to equal -2. What does x have to be? Well, if I added 3 to x, I need to subtract 3 in order to figure out what my new x is, right? So this, because I have to undo the operation on x, it shifts everything left 3 instead of shifting it right 3.
Okay.
So adding to the output works just like I would expect. It shifts up and down, right? Add and it shifts up. Subtract and it shifts down. Adding to the input, we have to undo the operations on the input. And so adding 3 shifts left 3. Subtracting 3 would shift right 3. Look me there? So the new point here would be -5, -8. This is -2 minus 3. Okay? So if I add, it shifts horizontally, it shifts vertically. When I do the input,
Okay, in order to see that, you need to shift left just a little bit. Thank you.
you add to the input and shift left. Transformations joke there. That's always good. Now, we'll talk about that. So, all right. So now that's addition and subtraction. What's going to happen if I multiply or divide? So I'm going to share my screen again. Okay. And go back to this one with Desmos. You know I like Desmos. So if I do a times f of x, okay, go back to my original function. Well, if I'm multiplying the outputs by something, you can see here, if I multiply by a number larger than 1, it stretches it, right? You see a vertical stretch. If I multiply by something less than 1, we get a vertical compression.
Is this
Multiply
the
by
input
what?
or the output?
Well, we're multiplying the output by something because we're multiplying f of x, the output, by a.
Okay.
Make sense?
Yes.
So multiply by 2/10, and every output value here it was 4/10, here it was 2. So it's 2/10 of what it was before, right? So everything's compressed toward the axis. If it's negative, then it works the same way, except you reflect. Does that look okay?
Yep.
So if now the next question then is, what if I multiply by the input? So do you want to make a prediction?
I think it's
If
going to
you
stretch
multiply
the opposite way.
It's going to stretch. You think it's going to stretch horizontally or vertically?
Horizontally.
I think you are making a very good conjecture. So it's going to stretch horizontally, but keep in mind, we still have to like undo this operation on x. Okay? So if I multiply by something larger than 1, it actually compresses horizontally. You with me there?
Mm-hmm.
If I multiply by something less than 1, it stretches horizontally. Okay. So I get a horizontal stretch or compression, but again, we have to think about that undoing. All right, I'm gonna stop sharing my screen. You're gonna come back and see me. So if I multiply or divide, I get a stretch or compression. Right? And inputs always are affected horizontally. Outputs are always affected vertically. Now, this is a lot to unpack for this one problem. And in fact, you don't need to unpack all this for this one problem, which we'll see in a second. I'm just using it as a chance to kind of review all this stuff. Does that sound okay? So I don't want to
unpacking the problem for multiple reasons.
What'd you say, Alyssa?
You're really unpacking the problem in all of its pieces.
I really am unpacking it in a lot of ways.
In the words of Dr. Barrel, you're flushing it out.
That's right. You really should sit in on 3370 class and see how much we unpack problems.
What is that?
Math in secondary school.
Oh, I've already taken that, so.
All right. So the thing you have to remember here is that we have to undo the operations on the inputs. Okay. Now, let's look at what this would mean here for this. If I have, say, 5f of x, well, then I can look at my point -2, -8 that I was dealing with earlier, and I can just plug in -2. And I know f of -2 is -8, so that's going to be -40. So my new point is -2, -40, right? And that was -8 times 5. Just multiply all the outputs by 5 like we wanted to. If I do f of 5x, on the other hand, if I put in -2, then all of a sudden I have f of -10, which is not related to that original point. So what I do instead is ask, where is it going to equal -8? Only equals -8 if this input equals -2. So I'm asking, where does 5x equal -2? Well, what do I have to do to solve that for x, everybody?
Divide by 5.
Yes. Again, that's us undoing the operations on x. So in order to compensate for the fact that I multiplied by 5 here, I have to divide my input by 5 in order to get the same output I would have otherwise. I'll say that again, because that was a lot there. In order to, because to compensate for the fact that I multiplied by 5 on the input, I have to divide my input by 5 in order to get the same output I did earlier. Okay? So my new point is -2/5, -8. That all sound okay? All that to say, if I have g of x equals f of 2x, what is that going to do? What does f of 2x do to the graph of f? All right, so I saw Melissa go like this, so I assume that means you think it affects it horizontally. All right, and now Blake has voluntarily decided to mute his so that he can make motions. It's outstanding. So I like, and Gabby says stretch horizontally. Do we all agree it's going to affect the graph horizontally? Because it's multiplied by the input, right? So since we're multiplying by the input, it's going to affect it horizontally. It's going to either stretch or compress. Which one is it going to do? Remember, we have to undo the operations on x, right? So I want to know, where does -8 equal f of 2x? F of 2x has to equal -2. So what does x have to be?
-1.
-1.
-1. Okay. So the point that's going to coincide to that one here, this 2 is actually a compression horizontally by 1/2. Okay. We have to undo the operations on the inputs. So the new point is going to be the corresponding point is what I'm trying to say, is going to be -1, -8. Okay. Yes, -1, -8. Now, the solutions the possibilities that it gives you here are -1, -8, -4, -8, -2, -16, -2, -4, 1096. Okay.
I think the 4,000 one is the correct answer.
Yeah, yes.
It's a little bit of a stretch.
Based on what we just did, it should be clear that that's the right answer.
Obviously.
Now, B is there to distract you by saying, all right, that's what's going to happen if you stretch horizontally by 2, right? Which is the tempting thing to want to say it does. This one is to think it stretches vertically. This one, I'm not sure exactly how you're going to get there, but it's going to take some work. These are good distractors. I'll say this. Even if you're unsure, if you get to this point and you're like, wait, is that a horizontal compression or a horizontal stretch? You can take advantage of some test-taking skills here and say, which one of these actually work, right? They should work in f of 2x. You know what f of 2x is. If f of x equals, if f of x is x cubed, f of 2x is 2x cubed, or 8x cubed, right? So
Can you scoot over just a little bit?
Yep.
Thank you.
So you should be able to just plug these numbers in and see which ones work. Okay. The -1 and -8 does work. -4 and -8 does not work. -2 and -16 does not work. And this one is a good distractor because if you do -2 cubed, you're going to get -8 times 8. Yeah, that one doesn't work either. So, so none of these work except -1, -8. So really, if you knew what we talked about with composition of functions, you could figure this out even without having to know all the transformation stuff. The transformation stuff makes it super easy to pick out the right answer. Okay?
So if you were taking this, like if you had this question, what would be your first approach to this?
Well, you know, that's a little bit, that's a personal question, Alyssa. And so, no, I'm just kidding.
My apologies. My bad.
You know, it does matter. I mean that in the sense that it does matter kind of what your personal understandings are, right?
Mm-hmm.
I mean, for me, I would look at that immediately and say, multiplying the input by 2, compress the input, compress horizontally. So I'd say divide all the inputs by 2. -2, -8 is going to be -1, -8. So I would think about it in terms of transformations immediately. But if I was a little bit unsure, I would double check by just plugging in and seeing which one works.
Okay. I was just curious.
Yeah. All right. We went over a lot of stuff there. Is that okay?
That's good.
Give me a thumbs up if you're all right.
I feel good.
Okay. Awesome. I want a virtual thumbs up from Gabby. All right. Let me thumbs up. Nice. All right. So let's look at another problem. Okay. 43. Oh, it's 43 is the number on the test. You don't need to know that. I'm going to erase all.
Blake, a minute ago when your dog barked, my dog started freaking out. He was like looking around the house for another animal.
Okay, I'll turn it down. I'm sorry.
All right. So the question is, a ball is dropped from a height of 120 feet. Okay. If each rebound is 3/4 of the height of the previous rebound, or sorry, previous bounce is what I meant to say. Which of the following functions would best model the ball's height as a function of rebound number n? Okay. Okay. There's a lot of information, a lot of reading here to kind of put all this together. But we're trying to choose a function type that's most appropriate for this particular situation that we're given here. Gabby says definitely something with n minus 1. I like that answer. Here are the possibilities you're given. Gabby, you're thinking about this. You're thinking about this recursively, which is a really helpful way, and we'll talk about how to get from recursive to explicit. The choices you're given are all explicit functions where you're basically trying to write the height as a function of n and not as a function of the previous height. So we have quadratic, polynomial, linear, and exponential. Okay. Gabby, as I turned around, your comment disappeared. So if you want to type that again, that would be helpful. I missed it. Does anybody have a strong feeling about which one of these you think is right? Oh, it was not an oops. It was a good It was a good suggestion, actually. We'll see in just a second. I don't know what that was.
A maybe?
You think it's A, quadratic? Okay. Why do you think it's quadratic?
Honestly, I don't know. I just feel like I'm more along the lines thinking of the ball dropping and the effects of the rebound up and then back down, and it would just get smaller.
Yeah. So that's a good insight, actually. Like if you were to model the height as it drops,
Right.
like where it's being acted on by gravity, that would be a quadratic function. Actually, it would. You would see it, the height falling more slowly and then increasingly fast as it goes on. What we have to be really thoughtful of here is what are our inputs and outputs. Gabby said she immediately thought exponential. If you can type it in a box, a reason for that, Gabby, I would be interested to see it. But I understand if you can't type that all in. We I have no idea, honestly. With a ha-ha, I like that. Can y'all see Gabby's comments when she says stuff, or is that just for me? Okay. So when we let's think about what our variables are here. One of our variables is what are the two variables we're told?
120 and 3/4.
Well, those are our numbers that we're given. They're not those are the variables we're given. Gabby says height and rebound number. She's exactly right. We're asked to say we're modeling the ball's height as a function of the rebound number. Okay? So we're told height and rebound number are the two quantities we're trying to relate here.
Okay.
If it says height as a function of the rebound number, then which one is being given to us? Which one is supposed to be input there? Is the height or the rebound number supposed to be the input?
Wait, what?
Yeah. It says that we have a function here, right? So we need an input and an output.
Yeah.
If it says height as a function of rebound number, which one should be the input and which one should be the output? Okay.
Would the height would be, right?
Would be what?
The variable.
It's one of the variables.
Yeah, that's the thing that's changing over time, over the number of bounces, right?
Yeah, so which one's independent variable and dependent variable? That's a good way to think about it.
Yeah.
Which one's independent?
So your bounces are independent. Your height is dependent.
Exactly. This language right here as a function of, if you have like y equals f of x, the standard way of saying that is we say y is a function of x. Okay? So that language you should be able to read as input output.
Yep.
So if we say p is a function of q, that means that p is some function of q. Okay? F of q should give me back p. Okay? That's just an aside here. So if we think about n, then is our input, that rebound number, and the height is our output.
Yeah.
we could probably build ourselves a little table here. What's rebound number 0? What's the height that we start with?
20. 120.
120. Rebound number 1, what height are we going to get?
It's
90.
3/4 of 120.
It's 90 because it's 120 times 3/4, right?
Yep.
And then to find the second one, what are we going to do?
Take
3/4 of
90
90.
times 3.
3/4 is 90. 90 times 3/4 is what?
60 something.
60 something. Yeah, so 45, 22.5. So it's 67.5.
Yeah.
Now, this we did
Guys.
120 times 3/4 times another 3/4. I probably need to move my screen here.
Yeah.
Okay.
There you go.
All right. And then if we were going to do the third one, you would just do 67.5 times another 3/4. In other words,
Yeah.
take 120 times 3/4 times 3/4 times 3/4. You with me there?
Yep. Oh, man.
This
I'm smelling
goes back to what you said. The way we've written this out is recursive. We're thinking about the previous answer. Yeah, when we say previous bounce, this is exactly right. We're multiplying the previous by 3/4 to build this right here, right? So that's why we're saying, like, recursively, take the bounce at n minus 1 and multiply by 3/4 to get this one. But if we want to think about what kind of function that builds, what kind of sequence is this?
Decreasing?
Decreasing, yes, absolutely true. What do you call a sequence where you multiply by the same thing to get from term to term?
Geometric.
Geometric. So this is a geometric sequence. Think about if you wanted to write a formula for this. This is 120 times 3/4. This is 120 times 3/4 times 3/4. This would be a lot easier to write if I just did 120 times 3/4
to the x.
Right?
Boom. Yep. Sure
Exactly.
enough.
Gabby's giving this to us. This one would be 120 times 3/4 to the 4th, right?
Yep.
And the height is just going to be 120 times 3/4 to whatever number of bounces we're looking at. Because that's the number of times we multiply by 3/4.
Yep.
There?
Yep.
Which is what type of function?
Exponential.
Exponential. Every time, okay, a geometric sequence is always described with an exponential function. Just like an arithmetic sequence where you add the same thing over and over is always described with a linear function, a geometric sequence is always described with an exponential function. And this highlights kind of the important characteristic of an exponential function. If you think about a linear function, the important characteristic of a linear function is every time you change x by the same amount, y changes by the same amount. Constant change in input gives you a constant change in the output, right? And you see that in an arithmetic sequence. Every time you increase the number of the term, you get the same change in the sequence. For an exponential function, it's not that the change is constant, it's that the ratio is constant. It's that we multiply by the same constant every time. Every time you change the input by the same amount, you multiply by a constant. In this case, every time we change the input by 1, we multiply the output by 3/4. So a geometric sequence, this sort of behavior where you multiply over and over by the same thing every time you increase by the same amount, that's always going to be an exponential function. Does that make sense?
Yep.
Okay. How do we feel about that? Thumbs up from Melissa. I like it. Thumbs sideways from Blake, I guess is what that is. Thumbs up from Gabby. Good. All right. We got everybody. All right. Again, This one is not one that I expect you to spend this much time on when you're taking the classes. It's just an opportunity for us to kind of review all that stuff right there. Okay. I'll change this slightly. If it had said, this is an impossible situation, but let's just say, for instance, if it had said each rebound is 20 feet less than the previous height, what type of function would we be dealing with there?
Linear.
Linear. It's heard it from a couple places. Yes. It's a linear function because then we have a constant change. Okay. Here we would see an arithmetic sequence. All right. Okay. Any more questions on that one?
What kind of problem would it be for quadratic or polynomial? Can you give us an example?
So polynomial could be lots of different types because polynomials a really broad range of functions. A quadratic, if it asked about the height as a function of time, where you have a constant acceleration, a constant rate of change in the rate of change, that would be a quadratic function.
So like the one where the guy was on, he climbed up to the slide and then he sat down. It was like height of his waist, I think is what we did in class.
Yeah, so if you did that, like the portion where he's sliding, like if you just took that portion, it should be since he's accelerating at a constant rate, presumably, assuming you have constant friction on the board and all that stuff, then yeah, that would be quadratic. What you'd expect to see in a sequence of quadratic is something like this. You know, a linear function, you might see something like this.
Right.
Right, where it's a constant rate of change.
Right.
For quadratic, you would expect to see something like this. Like, sorry, I have to think it through a little bit. If I said it was like, okay. So what we see here is the changes here are 20, negative 20, negative 25, negative 30, negative 35. So notice the rate, the change is not constant, but the change in the change is. You with me there?
Yes.
So if the second difference is constant, that's quadratic. If the third one is constant, that's and this goes back to calculus. Like you're basically saying if a linear function has a constant rate of change, so the first derivative is constant. A quadratic function, it has a linear rate of change, so it has its rate of change of the rate of change is constant. So the second derivative is a constant. With a cubic, you'd expect the third difference to be constant, the fourth difference with a quartic, so forth and so on.
Okay.
But that's sufficient for the Praxis there. That's all you really need. Okay, so if y'all are up for it, we can keep going until about 6 o'clock. So we probably have time for one or two more problems. Is that all right with y'all?
I'm probably gonna get off because we're supposed to go to dinner and a movie real quick.
That's
but
fine.
I will get with somebody for notes and watch the rest of it later.
Okay, that sounds good. Let me ask you before you go. I need to take a poll before we do these. Helpful, not helpful?
Very helpful.
Okay. This format works decently well for you, Alyssa?
Yeah, pretty well.
Okay. All right. Well, we'll see. If you have any comments on how to make it better.
Only question I have is what other topics do you think we're going to cover?
Well, that was the other question I wanted to ask you guys about what topics you would like to see covered. Sort of the way, and we already have one outline. We have one person set up to do statistics. Dr. Martin, so Dr. Sahin was going to do something on statistics. Dr. Conrad is going to do one on like ratio, proportion, and percents, which come up a lot and are something that people seem to struggle with. Dr. Martin's going to do one on calculus.
Yeah.
Calculus? Okay.
Heck,
And then I think we need to do a couple more on like algebra and maybe geometry. Gabby, you've
Yes,
taken
geometry for sure.
Geometry for sure.
Yes.
Geometry definitely. Okay. I wasn't sure on geometry because the geometry portion is less than the algebra portion. But, I mean, it's still something you need to know.
and
So I
definitely,
think Dr.
but
Watson
there's
was-
just so much algebra that we just don't really see once we get up. You know what I mean? You just forget a lot of it.
So Gabby, if you'll tell me what your highest priorities are, I will try to schedule the ones you request before your test date since you're taking it soonest. I'll try to work that out.
Yeah,
But
yeah,
Alyssa, if you have to go, that's fine. Yeah, that's absolutely fine, Gabby, as well. And Alyssa, I'll see you tomorrow as well. All right, let's go to. So if you guys are going to stay on, I'll do another problem real quick before we.
I'm good to stay.
Okay.
Bye, guys.
All right. See you, Alyssa.
Bye.
Okay. So, which was the one I was going to do? Okay. Let me erase. Okay. So the question here was the graph of y equals x to the fourth minus 81. It's a fourth up here. X to the fourth minus 81 over x squared plus x plus 12. Okay. Or sorry, minus 12. Has how many asymptotes? Okay.
Doesn't this one involve the exponents of the top and the bottom?
Yes. So yes, it does involve the exponents of the top and bottom for horizontal asymptotes.
Okay.
So for horizontal asymptotes, what we need to think about is, remember, horizontal asymptotes are about what happens as x gets really big. Okay.
Okay.
So all we really care about is what happens for extreme values of x for horizontal asymptotes. Okay? For really big values of x in a polynomial, the only thing that matters is the leading term. Because basically, if you think about x squared plus x minus 12, for instance, if you're putting in a million or a billion, 1 million squared is a million times greater than just x, right? Than a million. So the leading term is so much bigger that for extreme values, those dominate, and the other terms just are a drop in the bucket compared to that. Okay? So for the horizontal asymptotes, all we have to think about is as x goes to plus or minus infinity, y is going to look like x to the fourth over x squared. Right? And so what's x to the fourth over x squared reduced to?
Well done, Tom.
2.
See you later.
Well, x squared, I think is what you mean.
Yes.
Tom, the total
Which has no asymptotes, right? Like x squared does like this, all right? Now this does tell me like end behavior, like when you start thinking about end behavior of polynomials or rational functions, you can say that like as x goes to infinity, y is going to go to infinity, and as x goes to negative infinity, y is also going to go to negative infinity because it looks like x squared on the ends, right? So it goes up on both ends.
is something wrong.
So there are no horizontal asymptotes here.
Right.
If we had something like, let's say it was x squared minus 81 over x squared plus x minus 12, then y would approach x squared over x squared, which is 1. So y equals 1 would be a horizontal asymptote.
Okay.
Okay. If it was x minus 81 over x squared plus x minus 12, then y would approach x over x squared, which is 1 over x, which goes to 0 as x gets really large.
Oh.
So y equals 0 would be our horizontal asymptote. Sorry, my board work is a mess over here. Is that all okay?
Yes.
Melissa, you with me on that one?
Yes.
Okay.
Perfect.
Gabby's remembering it now. That's why, you are right about, like, just compare the degrees, or, like the degree of the top and the degree of the bottom. Basically, if the degree of the top's bigger than the degree of the bottom, then you're going to be left with something like this, and you're not going to have an asymptote. If they're the same, they're going to reduce to a constant. And so you have a horizontal asymptote at that constant. If
Okay.
the bottom's bigger, you're going to have 1 over something that grows, so it's going to go to 0.
Okay.
So you can reduce it to a rule, but to me, if you just know the biggest term is what matters, all that just falls out from knowing it. Okay? So if you know the
Okay.
biggest term is what matters, that tells you in behavior of polynomials, it gives you in behavior of rational functions. It's all you need to know to figure all that out. Okay?
Okay.
All right. Now, back to this question, which is really what we're concerned with, is I really want to know about the vertical asymptotes. Since there's no horizontal asymptotes, I really need to worry about the vertical asymptotes. So when will I have a vertical asymptote?
I'm clueless.
Okay. Gabby, you got anything? No response. I want to factor, but I'm not sure. I like your intuition. Factoring is a good idea. Think about what a vertical asymptote means. A vertical asymptote is basically a place where the graph is undefined, right? Like it's growing without bound, right? Or it's going to positive or negative infinity without bound. So where that's going to happen since polynomials, back up. A rational function is just a polynomial divided by another polynomial. So polynomials are defined everywhere. They work whenever. So the only place I'm going to have a problem is where the fraction is giving me trouble, like where the denominator is undefined. If the denominator is undefined, then we're going to have something goofy going on. Okay. So what I want to do is figure out where is the denominator 0. I said undefined. I meant to say where the fraction is undefined is going to be where the denominator is 0. Sorry for misspeaking earlier. When the fraction is undefined, the only way that's going to happen, since polynomials work so nicely, is for the denominator to be 0. So factoring gives us a nice way to figure out where the denominator is 0. So I can do x to the 4th minus 81 over x squared plus x minus 12, and I can factor that denominator into, there's lots of ways to factor, but basically I need two numbers that multiply to give me negative 12 and add to give me positive 1. So I'm going to do positive 4 and negative 3. Okay. If you like the box method, you remember we talked about in history, you could also always do that. X squared, negative 12, x and x, 4 and 3, negative, and then figure out if it works, regardless. So the denominator is going to be undefined at x equals negative 4 and at x equals positive 3. All right? Does that look all right? Now, this one's actually tricky. It means it looks like I should have two denominators. Or sorry, not two denominators. two vertical asymptotes. Let me graph the thing real quick, though, and show you what it looks like. Okay. So if I get rid of all these guys, because I don't want to see them anymore, and I graph my function, y equals x to the fourth minus 81 divided by x squared plus x minus 12. Okay. Well, if I sort of zoom out here, you can see, let me change this to go from, say, -5 to +5. Okay. You can see that, yeah, look at -4. I have a vertical asymptote just like I suspected, right? At 3, I do not. Why is that? Well, it turns out vertical asymptotes aren't just where the denominator is undefined. We also have to look at the numerator as well. We can factor this numerator. All right, let me stop sharing screen. Okay. We can factor this numerator. It is a difference of squares. X squared plus 9, x squared minus 9. Is that okay? And then if I can't factor this without complex numbers, but I can factor x squared minus 9. You see that we have x minus 3 in the top and the bottom? What that means is the function is undefined at x minus 3, but because it's a 0 of both the numerator and the denominator, Gabby asked, does that mean there's a hole at 3? And you're exactly right. X minus 3 over x minus 3, because it's 1 everywhere except at 3, makes no difference whatsoever for the graph. This looks just like x squared plus 9 times x plus 3 over x plus 4, as long as x does not equal 3. Okay? Everywhere except at 3, that thing doesn't make any difference whatsoever. At 3, it's undefined. But because it doesn't make a difference elsewhere, it means that there's no asymptote there. Okay? So vertical asymptotes are going to occur when the denominator is 0 and the numerator is not. Okay? So even if you didn't factor the numerator, you could know to check, all right, -4 and +3. Let's check. If I put 4 in there, I'm not going to get 0 in the numerator. But if I put 3 in there, I am going to get 0 in the numerator. So that is not a vertical asymptote. Okay. So vertical asymptotes occur when the denominator is 0 and the numerator is not. Okay. If I go back here to the graph, I can even trace this. Whoops, sorry, I forgot to click share.
Hey, Blake's trying to get back on. He said he can see us on YouTube, but he can't find the link. So how does he get back on?
Well, we're gonna tell him we're going to. I have to end right here anyway. So if he's watching on YouTube, that might have to be sufficient for now. He should be able to follow the link I sent in the email that he followed to get here.
That's what I told him.
Regardless, you can see that actually Desmos, if I look here, it does say it's undefined at 3. It shows that there's a hole there, but otherwise you can't tell because it looks just like that for every other possible point.
Right.
Okay. So, all right.
Okay.
Any questions about that particular problem or about rational functions and the way they work? I'll say one more thing about it. This right here, and this to a lesser extent, would give you your x-intercepts are zeros. When the numerator is 0, that's going to be an x-intercept for the graph because the whole function ends up being 0. So That's what
Okay.
important points for a rational function. Zeros in the numerator give you x-intercepts. Zeros are the denominators that aren't repeated up here. Okay, zeros in the numerator and zeros in the denominator give you x-intercepts and vertical asymptotes as long as they're not shared between the two. This idea that we did over here with the horizontal asymptote gives you the long run behavior, tells you what it does at the ends. And with that, you can get a pretty good sketch of what the thing ought to look like just with that information, you know, that degree of analysis. Okay, I have to end here for tonight. You're very welcome, Gabby. I'm glad it was helpful. Melissa, I hope it was helpful for you.
It definitely was. Thank you so much for your time.
Sure. So these should go up. We're going to put together a playlist on YouTube that should have a lot of these that you can go back and review. I'll be in touch with when the next one's going to happen. I'm still trying to get people to commit to dates. And then it'll work basically the same way. I will share a link with you guys, and then I'll just let the other person turn it up, take over the hangout and go from there. So sound all right?
Blake said thank you too.
Okay. Tell him I said you're welcome. It's good to see you guys. Melissa, I will see you tomorrow. Gabby, I hope I'll get to see you soon, and we'll talk soon.
All right. Good night.
Bye, guys.